So today we talk about vectors, right? And it's such a long section that we don't even have a starter question. We just get right into it, okay? Now, those of you that have had, how many of you had physics before or are taking it now? Okay, most of you, so you're at least familiar with vectors then, okay? For those of you that haven't, we're going to kind of start from, from the bottom up, okay? We'll introduce vectors, explain what they mean, okay, and kind of go from there, all right? All right, so, okay, so a scalar then, remember, a scalar is a quantity that measures only, distance or in vector speak, it's called magnitude, right? Whoa, that's not the color I wanted. Magnitude, okay? And it's simply it's just a plain old number, right? Okay, so examples would be like pounds, okay, 5 pounds, 40 miles per hour, something like that, okay. All right, now a vector, okay, is a quantity that measures, it measures magnitude, but it also measures direction. Okay. So now again, so that's just a plain old number with a specific direction. Okay. So this one, to go with our other examples, we could have 5 pounds at, I don't know, 90 degrees or something like that, okay? We could have 40 miles per hour going east. Okay. So it just adds another component to that, all right? Okay, so when you talk about geometric representations of vectors, okay, so we're going to graph these and plot them and all that kind of stuff, okay. So a vector can be represented by a directed, what we call line segment. Okay, because vectors have a specific direction and they have a specific length. Okay. All right. Okay, so let's go through some of these here and start drawing vectors, and then we're going to talk about different parts of the vector before we get going here. Okay, so it says draw the vector AB if A is at 0, 0, and B is at 3 and 4. All right, well the 0, 0 part's pretty simple. Actually, they're both pretty simple. All right, here we are at 0, 0, and then if we go to 3 and 4, okay, we're right in this area here. So now the vector, we're going to have it look like this. Oh, that doesn't look very well. Okay, that should be an arrow point. It doesn't look very good, but you get it. Okay. Now, so let's talk a little bit. All right. So with the initial point is just our starting point. It's where we start, and in this case, it is at 0, 0. Okay, well the terminal point is the ending point. Okay, or in this case it's 3 and 4. Okay, now the magnitude is what? What does that represent? Yeah, how long the vector is. Okay. And it is written this way. Okay. So we would write the magnitude of vector AB. So it looks like that. It looks kind of like, remember when back in 1015 we were talking matrices about the determinant. Thank you, the determinant of a matrix, right? It's got that same symbol. That's a B. It's a really bad B. There we go. Right, we're dealing with AB up here. Come on, people, work with me here. Work with me. Okay. Yeah, so again, so the magnitude is just simply the length or how long it is. Okay. What's that?
Is it 5 because it's 3, 4, 5, 9 more?
Okay. Well, yeah, we're yes, and we're going to talk about that. But you're exactly right, Connor. Okay. Now the tip, all right, is simply the terminal point, okay? And you'll hear, you know, we'll talk about tail to tip and stuff like that, so. And then the tail is the initial point. So we start at the tail and we go to the tip. All right, so now let's talk about, again, let's talk about the magnitude for a minute, okay? Because we have, we can make a right triangle here, okay, like Connor said, okay, and this is 3 and this is 4, okay? So how would you find that, the length of that? Yeah, it's using Pythagorean theorem, right? Not because we formed a right triangle, okay, so that's not a big deal. So in this case, this magnitude is 5, okay? Now, the direction angle, okay, which we will call theta here, okay, how are we going to find theta? Okay, and let's use our trigonometry here.
Well, isn't it a special, right? It's 36.
Okay, could be, not necessarily though, and I want to put this in general terms, okay? So we don't necessarily want to rely on that, okay? What do you think?
Take the arc sine or cosine or tangent of B.
Okay, and we're gonna do arctangent since we don't, since we're not given the length, now now that's obviously easy to find, but we wanna put it in terms of tangent here. So we're gonna say the arctangent of theta, I'm sorry, theta is equal to, let's erase that. So theta is equal to the arctangent, in this case, of 4/3. Okay, so you plug that in a calculator, and you wind up with, let's put it in degree mode.
53.1.
Thank you. Okay, 53.1 degrees. So that is our angle there. Okay, and we'll talk more about finding angles, especially when we get two vectors and we're going from there.
So why did we use the arctangent and not just like, because if we knew that the hypotenuse was 5, why couldn't we use like sine?
Yeah, you could have.
We could.
But we just wanted to define this in general terms for all of them. So if we don't know the hypotenuse, okay, then we can still find the angle. So yeah. Okay. All right. So different. So these are different notations that you will see for vectors. Okay. And that is an arrow, like an arrow point there. Okay. Now if it's bolded, all right, in lowercase, it'll look like that. Okay. And like this means the same as this one here. Okay. Or it could just be capital bold letters. And again, vectors are generally bolded. I can't remember what MathXL does with those, but you'll find out soon enough, apparently. If I remember right, they are bolded lowercase letters. Okay? All right, so let's talk about equal vectors. So vectors are equal only if they have the same what?
Direction and the same
Yeah, the same magnitude and the same direction. Okay, so let's draw each of these vectors here. Okay, and then we want to state which vectors are equal. All right, so A is 0, 0 to, or AB is 0, 0 to 3, 4. That's the one that we just drew. So there's 4, so roughly right there. Okay, and that's AB. All right, CD is, we start at 4, 7. 1, 2, 3, 4. And 7 is right here, well, roughly. That's C, and then D is at 1 and 3. So there's D. Okay, E is at 2 and negative 1, and F is at 5 and 3. And then GH, G is at -4 and 1. And H is at -6 and 4. Okay, there's GH. All right. So there are all of our vectors. Now, which two look to be equal? Which two have the same magnitude and same direction? So again, that would be the same length and same direction. Okay, if I had drawn a little better. Yeah, AB and EF. Now, it's pretty apparent they have the same direction. If you want to check the same magnitude, okay, then you can calculate their magnitudes. In fact, we're going to talk about that, okay? All right, so now, so with that then, so if AB and EF are equal, okay, that sliding a vector around then does not change its magnitude or its direction, correct? So I could take AB, slide it into EF, or vice versa, okay, and I'm not changing the magnitude or direction of that vector. So we write that down, the magnitude or direction. Okay. All right, so now since this is the case, we can slide each vector so the tail is at the origin, which we always like, right? Now these are what are called position vectors, okay? Because they all start in the same position with the tail at the origin, okay? And you also hear that called a radius vector, but not very often. Usually the general term is position vector, okay? Now obviously this makes it easier to compare vectors because they all start in the same place, okay? And this is going to lead us to the idea of what is called component form of a vector, okay? Now component form is useful because it allows us to write vectors using only two pieces of information. We have what we call a horizontal component and a vertical component. Okay, now the important part of component form, okay, is that it looks like this, all right, with that particular type with those particular types of brackets, okay? When you see those brackets, then you know that our vector, that we have a vector and it's in component form, okay? Now in this case, A is what we call the horizontal component, and B is the vertical component. Kind of like your X and your Y, if you will, okay? But with component vectors, okay, it's A and B. Okay, all right, so if we want to write this vector in component form, okay, it's best accomplished by subtracting the tail from the tip. Okay, because with this one here, all right, if we draw so to scale, do your sheets have a little XY axis over there? No? Oh, okay. Just wondering, because this other one does. All right, so if we write A and B, so A is -2 and -1, and B is, what was B, 2 and 4? 1, 2, and 1, 2, 3, 4. All right, so, whoa, seriously. So there's AB right there, okay? But we want to put that in component form. In other words, we want to slide it so that the tail is at the origin, okay? And again, the best way to do that, if you're in component form, is just subtract the two, okay? So we subtract the tail from the tip. All right, so since it's AB, now again, with vectors, and I didn't point this out earlier, okay, the order is important, okay, the order that's written in. So this tells us that A is the tail and that B is the tip. Okay. All right, so to subtract these then, we just go 2, 4 minus -2, -1. So 2 minus a -2 is 4, and 4 minus a -1 is 5, and that is our vector in component form. Okay. So if we were to rewrite that, I'm gonna freaking erase for the lip. Let me erase it so it does good. Okay, so now our vector would just look like this. So it'd be right, yeah. Anyway, right there, okay? And that's the vector in component form, okay? And at that point, we could find its magnitude, direction, all that stuff, okay? All right, so now we want to find the magnitude of this one, okay? So again, the magnitude, all right, is just simply the square root of the components. So it's 4 squared plus 5 squared. And that's how you find the magnitude. And so that's a huge advantage of component form, okay? Finding the magnitude is really simple. You just take the square root of your horizontal component, and the square root of your vertical component. Or, sorry, the square root of the sum of their squares. So we get the square root of 41. Again, that's equal to the magnitude of AB. And again, magnitude written like that.
One of left to root 41.
Yeah. And unless it asks for a specific decimal, you know, if it asks for a decimal, then just leave it in exact form.
What is the first out of the square root?
Okay, it's the square root of 4 squared plus 5 squared. Right, so essentially what we're doing is we're using the Pythagorean theorem, because we've got, this part is 4, this part is 5, so we can use the Pythagorean theorem to find that length, basically, and that's what the magnitude is, okay? All right, so now we want to find the direction angle. So we want to find theta. So again, so theta then, is, remember, is equal to the arctangent. In this case, it's of opposite over adjacent, so 5 over 4. So what's...
You basically always use the arctangent.
Yep. Yep, you will. Okay.
51.
Again, 51 point, oh, did we do that one before? That sounds familiar.
This is just a teeny bit bigger triangle than the first one.
Oh, yeah, that's right, that one was 4, yeah, you're right, good call. Okay, all right, so, so far so good with component form, okay, not a big deal. Now, if we look at example 4, okay, now this time we're given the magnitude and our angle, and we want to come up with component form. So we need to put example 3 in reverse, basically, okay? So now if we were to draw this, okay, so this length is 5.6. All right, that's our right triangle, and then theta here is 22 degrees. And that's theta right, this angle right there, okay? All right, so to find the component form, we need A and we need B. So how would we find A and B? Using our trig knowledge.
Yeah, the 90.
Okay, so that's a right triangle, correct?
Plug in
So,
2 equals B over 5.
right, so like the cosine, for example, of 22, like you said, equals B over 5.6. So B is equal to the cosine, I'm sorry, A, did I say, yeah, I did say B, and I wrote B even. Let's try A, shall we? So then A is simply equal to 5.6 times the cosine of 22. Which is, wait, it's coming to me. Say 5.19. I know, seriously. One day, Al, you'll be brilliant like me. Okay, so then what's B equal to? 5.6 times the sine of 22. Good. Which is going to give us, I'm thinking 2.09.
0.097, so 2.10.
Way to steal my thunder. So 2.1. Okay? And again, so that's so we write that in component form, put your little things there, okay? Now, if they wanted exact form, okay, or an exact value and not a decimal approximation, then component form would just look like this. This would be 5.6 cosine 22, and then 5.6 sine 22. And it would look like that, okay? So now this is going to lead us to a general formula, right? So we have the magnitude of our vector, so we'll just say the magnitude of v times the cosine of alpha, or theta. Sorry, let's use theta here. And then for our that's our horizontal component. And then our vertical component is the same, the magnitude of v times the sine of alpha. Okay? Alright, so hopefully that should look a little familiar.
Is that alpha or theta?
Theta, sorry, I keep saying alpha, but then I write theta. Yeah. Okay, because cosine's with x, sine is with y, right? So when we talk about those things, that all hopefully will interrelate in. Okay, let's talk scalars. All right, and we all know what scalars are, right? We talked about that in 1050 with matrices and stuff like that. It's just a number out front that we multiply on through. Okay, and scalar really is, it's the same thing. Okay, with vectors as it is with matrices. Okay, so now scalar is going to make the vector longer. It's going to make it shorter. Okay, it could have it keep the same length if your scalar is what? Yeah, if it's 1, right? If your scalar is 1, it's going to stay the same length. Or it can even make it go in the opposite, make our vector go in the opposite direction. Okay, depending on the value of our scalar. Okay, so so if we have 2 times the vector 3, 4, then that just simply becomes 6 and 8. Okay, don't overthink the scalar stuff. Okay, negative 2 times 1 and 1 becomes negative 2, negative 2. And then the negative times 1, 1 just becomes negative 1, negative 1. And that's what's called the opposite. Okay, whenever you throw a negative out there, that's the opposite vector. So what it does is this, okay? So if I have 1, 1, say it looks like that, right? There's 1 and 1. Okay, that negative is just going to send that vector in the opposite direction. So it's going to send it this way right here. Okay, well, that's negative 1 and negative 1. Okay? So that's scalar. Pretty easy stuff. Just remember, negative sends it in the opposite direction, the exact opposite direction. Okay? All right, now vector addition. Okay? Pretty easy stuff. You add 2 or more vectors together and you produce what's called a resultant vector. And you can do that, you can find a resultant vector 3 different ways. You can use, and the easiest is probably the tail to tip method. Okay? And then you can use it geometrically using what's called the parallelogram method, and they're all really accomplish the same thing. The easiest one though is probably if the vectors are in component form, you just add them up. Okay, pretty easy stuff. All right, so example 6 now, we do have vectors in component form. So we have vector u here and vector v. So we want to find, part A, we want to find u plus v. Okay. So u plus v then gives us, again, we just add them together. So we get 2 plus 5 is 7. And we get 3 minus 2 is negative 1. Okay? Or positive 1. Gosh, sorry. Positive 1. Let's see if we can rewrite that. 7 and 1. Okay? So now, if we were to write u here, so u is at 2 and 3. There's that. So there's u. And then v is 1, 2, 3, 4, 5, and negative 2.
Why is it 7?
Okay, and there's V. Okay, 7 because we have, you just add those together.
Adam, I think so.
Yeah. No, it's U plus V.
Oh.
Yeah, yeah, this is, yeah, we're not, yeah, this is just the resultant vector, so we're adding those together, right? So if we add those together, so then we get 2 and 5 is 7. And then 3 minus 2 is 1, so we are right here. So in other words, okay, if I took vector V here and I put the tail of V to the tip of U, okay, it would look just like that. And if you notice here, as we're going, what are we we're forming a parallelogram, essentially, okay? All right, so now if we had U minus 2V, okay? So the first thing we have to do is get 2V, right? So then we have, so U is 2 and 3, and then minus 2V would be, okay, it'd be 10 and negative 4. So 2 minus 10 is negative 8, and 3 minus a negative 4 is 7, and there again, there's your resultant vector. So we're at negative 8, and at 7. So roughly right there. Okay.
So is there any time where this tell method won't work and we'll have to?
No, because the parallelogram is essentially really just is a tip to tail. And what happens is when you take the tip of the one and put it to the tail of the other, then that, you're forming a parallelogram, basically is what you're doing, so. Okay. All right, so now, again, if you just look back at example 3, okay? The original vector is just simply the sum of the horizontal and the vertical components. Okay, so to finish this page off here, all right, just some notations, okay? And again, notice everything here is in component form, okay? And you're going to see that a lot, because component form is the easiest to work with vectors, okay? So if vector A is here and B is here, all right? Then scalar product, we take the scalar K, we just multiply it through, both to the horizontal and the vertical component. Add them together, add your horizontal components, add your vertical components. Easy stuff. The difference, subtract it, right? We all know that. Now, the next thing that we'll want to start talking about now is what is called the dot product. Oops. Of a vector, okay? And notice we take, so with vector sum, we multiply, where we added them, vector difference, we subtracted them with the dot product, or you could say vector product, but it was shortened to dot product. You simply multiply the horizontal components and the vertical components, and then we add them together, okay? So again, a dot product, again, is similar to the discriminant, I did that again, with matrices, to the determinant. Why am I calling that discriminant today? To the determinant of matrices. Okay, so a dot product is simply, it's like a scalar, okay, that contains information about the magnitude and direction of both vectors. Okay, so finding our dot product here. Okay, so remember from our formula back before. So U dot V is simply 2 times 5 plus 3 times negative 2. So it gives us 10 minus 6, or our dot product in this case is 4. All right, now, if we use the law of cosines here, okay, and really, that's all there is to dot product, okay? Don't, don't make this hard, okay? So you multiply your horizontal components, multiply your vertical components, and add them up. And that's how you get your dot product, okay? Now, if we want to find the angle between two vectors, okay? Now, if we have a vector in component form, okay, it's pretty easy to find the angle with the positive x-axis, right? We've done that. That's, where we use our inverse tangent, okay? But if we just have two vectors, two general vectors, okay, here's how we find the angle, okay? And using the law of cosines, all right, it becomes this. So if our two vectors are a and b, then it's going to be this. So the angle between them is the arc cosine of the dot product, okay, divided by the magnitude of each vector. Okay. So it's the inverse cosine of the dot product over the product of the magnitudes. Okay. Now a little note down here, okay, if you had books, which you don't, but it is different than the one given in the book. And the one in the book, they just don't take the arc cosine. So the one in the book looks like this, okay, or that you might see. So it's the cosine of theta equals a dot b over the magnitude of a times the magnitude of b. Okay, that's what the one. But we always want to solve for theta, right? If we're looking for an angle, so we just take. You got to take the arc cosine of both sides. Now, just to review, what is the domain of the arc cosine? That's from 0 to 180. So this guarantees, okay, or excuse me, that's the range, okay, guarantees us a positive angle between 0 and 180. Okay. All right, so let's do this, shall we? So we're going to find an angle between u and v, or find the angle. If u is 2 and 3, at 2 and 3, and v is at 5, negative 2. Okay. All right, so we just plug and chug, right? So theta is equal to the arc cosine of u dot v over the magnitude of u times the magnitude of v. All right, so what is our dot product here? So our dot product is 2 times 10. Oh, that's the same one, right? Okay, so our dot product is 4. So we have the arc cosine of 4 over, okay, what's the magnitude of u? And again, remember the magnitude is simply the square root of 2 squared plus 3 squared. So that gives us, what, root 13? Okay, and then the magnitude of v is 25 and 4, 29 times root 29. Okay, plug and chug. Okay, approximately 78.1. Everybody concur with that? Yes, no? 78.1? Okay. Then we will go with 78.1 between two vectors. Okay. All right, so the final idea in this section is the concept of unit vectors. Okay. And unit vectors are vectors that are 1 unit long, right? Hence the name. Like our unit circle, the radius is always 1. Unit vectors, okay, their length is always 1 unit. So, 1 unit long. Okay, so now the standard unit vectors are I and j. Okay, and again, notice that they're in component form, where I is simply 1 and 0. So I is your horizontal component, and j is your vertical component. Okay. All right, so unit vectors can do several things for us. They provide us a coordinate system and a standard notation. A unit vector in any direction is easily recognizable because it's got a length of 1. Okay, we can rewrite them using the standard unit vectors. So, for example, okay, So v is 5 and negative 2. Okay, the unit vector is just simply this. It's 5i, and it's negative 2, so it's minus 2j. And that's what a unit vector will look like, okay? And they're also, if we know that they're 1 unit in length, and they're easy to work with, and they are, of course, useful in calculus, because all this goes towards calculus, right? So like our 5, negative 2, okay? So again, so we go 5 in the I direction, okay, or again, 5 is our horizontal component, so we're positive 5, so we're 1, 2, 3, 4, 5, and then minus 2j. And there is, okay, and there is this vector right here, okay? Now, oh, hang on. Okay, so if we want to take this vector 4, negative 3 and write it, so we want to write that as a linear combination of I and j, and then we want to draw a representation, and then we're going to find the unit vector in that same direction, okay? So, linear combinations, pretty simple, so that is simply 4i minus 3j. Okay, we can graph that, 1, 2, 3, 4 in the I direction. So in other words, so what we're doing is we're saying we're taking 4 unit vectors that way to the right, okay, and then 3 unit vectors down. Okay, so that's going to put us about right here. And there's 4i minus 3j. Or 5, yeah, 3j, sorry. Okay.
So it's basically the same thing as a normal one,
Yep.
you're just counting it in units?
Correct. Okay. All right, so we've done that, pretty easy stuff. Now I want to find the unit vector in that direction. Okay? So now for the unit vector then it's simply this, all right? We take our original vector, so v1 and v2. Okay? And then we just divide that by the magnitude of v. Okay? So so if we find the magnitude there, that's a square root of what, 16 and 9, 25, so it's 5, right? So the magnitude is 25, so that is 5, so we get 4 over 5 and then negative 3 over 5, and that is the unit vector in the same direction as v. So again, unit vectors is just one unit long. Okay. All right, we okay with that? Questions? Good? Okay, I know this is long. We got one more. Okay, so now let's just now we're going to kind of put all this stuff together, start working with these, working vectors, drawing vectors and stuff, and then we got one more idea to cover, and then we're done. Okay. All right. So now for these pair of vectors, we want to draw the vectors a plus b and a minus b. All right. Well, now here, okay, we don't have what the specific vectors are. So here is where you can use the parallelogram method if you need to. But now since we have our coordinates, we can find our vectors. Okay. Now these are both position vectors because their tails are at the origin, correct? So, a couple ways that we can do this, all right? So now one thing I can do is I can take vector B and I can do the tail to tip method. Now, vector B, the horizontal component is 1, 2, 3, 4, 5, and the vertical is 2. So I can come now, if I do the tail to tip, or tip to tail, excuse me. So there's my tip, and I'm going to put my tail right there. So I'm going to go 1, 2, 3, 4, 5, and up 1, 2. Okay, put that right there. And then that is right there. That's my a plus b vector. Okay. So in other words, what I did is I took vector b and I moved it right there. Okay. Now to finish the parallelogram, all right, then this is kind of that parallelogram method. This is vector A, I can move vector A right there. And notice that forms my parallelogram. But what I'm interested in is this vector right here. Okay, that is vector A plus B. Okay. All right, so now what if we wanted A minus B? So now what am I doing with vector B? So instead of, now, on our first one, okay, we did it, vector B was here, correct? That's vector B. So if it's minus B, now what am I going to do with vector B? Send it in the opposite direction. So instead of going right 5 and up 2 from the tip of A, I'm going to go left 5. 1, 2, 3, 4, 5, and down 2, correct. So there is, so that's minus B, if you will. Okay. So then our A minus B will, let's put that different. So it starts here, and we go right there. And that is A minus B. Okay. So you okay with that? So that's how we handle these if you're just given the graph, okay? Figure out the horizontal and vertical component of your vector, okay? And then you can just move it to the tail, excuse me, to the tip of the first vector. Questions? All right? Okay. Okay, so in the next example here, we have vectors that are in component form. Okay, and we want to perform our operations indicated. Okay, and then we want to write our vectors in component form. Okay, our solution vectors, our resultant vectors in component form. Okay, so we have R minus S plus T. So order of operations, right? We're back to Math 101 here. Okay, so first thing we have to do is we have to do S plus T. So S plus T then is, what is that? 3, negative 1. Thank you. And now we're going to subtract that from R, which is 3, negative 2. Okay, so what do we get? Yeah, 3 minus 3 is 0. And negative 2 minus a negative 1 is negative 1. So there's our vector right there. So that would be, so where would 0 net negative 1 be? Yeah, 1 unit straight down, right? Our horizontal component 0, our vertical component's negative 1, so just be 1 unit, whatever that is, straight down. Okay. All right, now, hang on, let's pause and shift. Okay, so now we want to determine whether each pair, these pair of vectors is parallel, perpendicular, or neither. Okay? So let's think about this for a minute. So how can I determine if two vectors are parallel, perpendicular, or neither? What could we do? Okay, we could draw them up and look at it and see. Maybe. Okay, slopes, we're getting there, not quite. Okay, if I've got two vectors, what formulas do I have that we can use two vectors? Marissa?
Would you find the magnitude?
Okay, no, the magnitude, it doesn't matter as far as the angle in between them. Or oh, I just gave it away, way to go. Yeah, I want to find the angle in between them, right? That'll tell us, because when we're talking if vectors are parallel, perpendicular, or neither, we want to figure out what their angle is. If they're parallel, what's the angle between them going to be? That's going to be 0, right? Okay, what about if they're perpendicular? Angle between them is going to be 90. Okay, if they're neither, the angle between them is going to be something else. So what's our formula for the angle? Find the angle between two vectors. Do you remember?
It's the dot product.
Okay, yeah, it's the inverse cosine times the dot product. We'll call them A and B over the product of their magnitudes. Okay? All right, so our dot product is, what's our dot product? Okay, it's, our dot product is negative 12 plus 12, so our dot product is 0. Okay, now, so now it really doesn't matter what their magnitudes are, right? Because it's gonna be 0. So what's the arc cosine of 0? What is it? It is 90 degrees. So these are perpendicular. Now, for whatever reason, there's a special name when you're dealing with perpendicular vectors, and that name is orthogonal. Okay? So if two vectors are orthogonal, that just means they're perpendicular. Okay. Okay, so now just a quickie review here. What's the cosine of 90? 0. What's the arc cosine of 0? 90. Okay, so what is the only way that the arc cosine of A dot B over their product of their magnitudes is 90? If the dot product is 0, right? So that's kind of a quick way to check that first, all right? To check those two vectors, okay? Okay, look at the dot product first. If the dot product is 0, then you know that the angles or that the vectors are orthogonal. Okay? All right. Questions? You okay? All right. We are done.